The next state we'll be taking care of is the jumping state, as we now have everything we need to add it to our system. Before we start doing that though, we of course need to know how jumping works in Genshin. There are several outcomes when it comes to jumping, depending on the current player input or state. The most basic jump is when idling. This will add an upwards force and make the player jump in the same place, without moving horizontally. The outcome that follows it is jumping while moving. This will still add a normal upward force, but also jump towards our movement direction. One thing to note is that Genshin seems to have a different force for each moving state. This force doesn't seem to have anything to do with the speed modifier or with the velocity that our player is moving at. Another outcome is when rotating. We have already seen this previously, but if we press space when we have a movement input key pressed, then the player will jump towards the movement input direction. If we jump to the opposite side, then we'll rotate our player and jump towards that side. We also know from our automatic rotation part that it takes 0.02 seconds for this rotation to happen. If we pressed a movement key and unpressed it right after, if we end up pressing space while the player is still rotating, then the player will stop rotating and jump towards its facing direction. This is because the stopping states will have their own forces. Of course, if we were back to the idling state already, we will jump in the same place. And last but not least, we can jump while on a slope. In Genshin, when on a slope, we jump with a lower force. This is because if we were to jump with our normal force when we are facing a slope, it will be too much of a force and we wouldn't really jump but instead slide on the slope. This of course happens when moving, as we are adding an horizontal velocity towards the slope. Now that we know the possible outcomes of the jumping state, we'll start by creating its input. To do that, head over to the docked Input Actions window. In here, we'll add a new action named Jump. If Unity added the old interaction to it, feel free to remove it. We can leave the action type as button. For our binding, we'll listen for the spacebar key. When that's done, feel free to save the asset. Next, we'll create our jumping state script. To do that, head back to the Player States Scripts folder. In here, create a new folder named Airborne. Inside of the Airborne folder, we'll create two new C# scripts, Player Airborne State and Player Jumping State. Start by opening up the Player Airborne State script. In here, remove the default methods and swap the inheritance from Modifier to Player Movement State. Generate the necessary constructor as well. When that's done, open up the Player Jumping State script. Remove the default methods and swap the monobehavior inheritance with Player Airborne State instead. Make sure you generate the necessary constructor. We now need to cache the jumping state, so open up the Player Movement State Machine script. In here, create a new property for our jumping state. Make sure you initialize it as well. With that done, go back to the Player Jumping State script. When jumping in Genshin, we aren't able to move, simply meaning there's no air movement like there is when gliding. We can easily not allow movement in our jumping state by setting our speed modifier to 0, so override the enter method. Then, inside, type in stateMachine.ReusableData.MovementSpeedModifier equals to 0f. I'll add this method when we reach the named iStateMethods. We can now start thinking on how to add the jump force. The first thing we need is the force that we'll want to add when jumping, which changes depending on the current player state. To create it, head over to the player state reusable data script. In here, under our author vector trees properties, type in public vector3 current jump force and give it a public set. Now, because we'll be assigning this property value to a temporary variable, we don't really need to do the same thing we did in our other vector3 properties. This is of course because we'll not actually update the x, y and z of this vector3, but only the one of our temporary variable. With that done, go back to the player jumping state script. In our enter method, we'll now call in a new method named jump. I'll add this method to a new region named main methods. We'll start by assigning our current force into a temporary variable. So type in vector3 jump force equals to statemachine.reusabledata.current jump force. The reason why we are adding a temporary variable here is because the jump force will need to be changed depending on the slope angle as well as the jump direction. For example, let's say we want to add a force of 3 in the horizontal axis. 3 will always be a positive force, which will always jump towards the same side, even if we intended to jump in the opposite direction. We'll need to update it to be relative to our desired direction, which we might need to make it become -3 instead. We'll also need to reduce it when on slopes to be a certain percentage of the original force, which requires us to hold that original force somewhere. By creating a temporary variable, we can update it as we desire without updating the original property value. With that in mind, we'll now add our force by typing in statemachine.player.rigidbody.addForce and pass in jump force. We'll also be setting the force mode to be forceMode.velocityChange, as it shall be both time and mass independent. Of course, we need to update our jump force to be able to jump in the direction that our player is moving and not towards the positive force direction only. Not only that, but currently if we set a force of 3 while we are only moving in one of the horizontal axes, we'll still jump towards both horizontal axes, as we are adding a force of 3 to both axes. To solve these two problems, we can simply multiply our jump force with the player forward vector3. The player forward is basically our player normalized direction, which is the equivalent of where our player is facing. This means that if we are only moving in one horizontal axis, the force of the other axis will be multiplied by 0, which means we won't jump towards that direction. To be able to do that, just before adding our force, type in vector3 player forward equals to statemachine.player.transform.forward. Then we multiply our jump force.x with player forward.x and our jump force.z with the player forward.z. We don't want to multiply our y-axis as our player forward direction has no effect whatsoever in our upwards velocity. That's the very base of our jump done, and we can now jump with a given force. However, before we jump, we shall reset any velocity we have, as we don't want our current player velocity to impact our jump force. To do that, above our addForce method, call in reset velocity. This situation is one of the reasons why our reset velocity method sets the velocity variable right away for an instantaneous change. If we didn't do that, jumping multiple times in a row could make the player jump more than it should. Again, I'm not entirely sure why that happens, but I assume the order of the add forces is being swapped, or the force we were trying to add was now more than the player force at the time that the addForce method was actually called. Of course, we still need to create the data classes to be able to set the corresponding jump forces. To do that, save everything and head back to Unity. When you are there, go to the player states data folder. In here, create a new folder named Airborne. Inside, we'll create two new C# scripts: player airborne data and player jump data. Start by opening up the player jump data script. In here, remove the default methods and inheritance and make this class serializable. We'll be adding one property for each force strength. To do that, start by typing in field serialize field public vector3 stationary force with a private set. Then duplicate this property 3 times. Swap their names to weak force, medium force, and strong force. When that's done, open up the player airborne data script. Remove the default methods and inheritance and make this class serializable. We'll add a jump data property here by typing in field serialize field public player jump data jump data. I'll give it a private set. When that's done, open up the player SO script. Duplicate the existing grounded data property and swap the grounded with airborne instead. Once you are done doing that, save it all up and head back to Unity. We'll be setting our forces values, so open up the second inspector tab. In the airborne jump data area, we'll set the following forces. For the stationary force, we'll set y to a value of 5. For the weak force, we'll set the vector to 1, 5, 1. For our medium force, we'll set the vector to 3.5, 5, 3.5. For the strong force, we'll set the vector to 5, 5, 5. With that done, we now need to assign these values in the corresponding states. If we take a look at Genshin, we can see our forces being applied to the following states: idling, which gets set to the stationary force; walking and light stopping, which gets set to the weak force; running and medium stopping, which gets set to the medium force; sprinting, dashing and hard stopping, which gets set to the hard force. Regarding the forces, they also seem to depend on the size of the selected character. For example, smaller characters seem to have the same medium and strong jumping force, while taller characters seem to have a stronger strong force. Thankfully, if you ever need to differentiate their forces like that, you can simply create another scriptable object for smaller or taller characters. We will however not do that and just use our existing player scriptable object. Now, sometimes the stopping states use the stationary force at any given frame, and sometimes they use the weak, medium and hard forces at any given frame as well. I couldn't really understand what was the factor that decided which force to use, as it didn't seem to be at a certain frame. To make it easier for us, we'll leave the same force for the whole animation duration. If you did want to set a stationary force in a certain frame, you could do it by overriding one of the animation event methods and set the current jump force to the stationary force there. Upon further inspection after recording everything, I notice it will depend on the last jump we have made. So if we have jumped while idling, the stopping state will jump with that force. It wasn't the case for every single stopping state, as the lighter stopping states, for example, wouldn't transition to the stronger force. It seems to cause a bug sometimes where something like dashing and jumping would cause the jump to use a stationary force as well. So because I don't find this way of doing it to be correct, and mainly because I've already recorded everything, I'll go with my current implementation. If you do want to try to be as close as possible to the actual implementation, you will likely not set the forces in the stopping states. With that in mind, we'll now assign the forces in the corresponding states. We'll start with the idling state, but because we'll need to reference the Airborne data a few times, start by opening up the player movement state script first. In here we'll create a new variable by typing in protected player airborne data. Then in the constructor we type in airborne data equals to statemachine.player.data.airborne data. When that's done, open up the player idling state script. In the enter method, we'll set the jump force by typing in statemachine.reusabledata.currentJumpForce equals to airborne data.jumpdata.stationaryForce. When you are done doing that, copy this line and open up the player walking state script. Paste the line we just copied in the enter method and swap the stationary force with weak force instead. Copy the line again and open up the player light stopping state script. Paste the line in its center method. Next, open up the player running state script. Paste the line in the enter method and swap it with medium force instead. Copy the line again and open up the player medium stopping state script. In here, paste the line in the enter method as well. When you are done doing that, do the same for the sprinting, dashing and hard stopping states, but swap the medium force with strong force instead. That's it for our forces, so before we add the remaining features, we'll actually make it so that we can transition to and from the jumping state. This will allow us to test what we have done so far. Taking a look at our movement system states, we can transition to the jumping state through the following states. Every grounded state. This basically means that we can add a transition to the jumping state in our player grounded state script. So, knowing that, open it up. In here, in the add input actions callbacks method, found in the reusable methods region, we'll add a new callback by typing in statemachine.player.input.playeractions.jump.started plus equals on jump started. Don't forget to remove the callback as well. I'll make this method protected virtual and add it to the input methods region. I'll also rename the parameter to context. To transition to the jumping state, we simply type in statemachine.changeState and pass in statemachine.jumpingState. That's it for the transitions to the jumping state, so we'll now add a transition from the jumping state. For now, because we don't have the falling and the landing systems in our system, we'll simply transition to the idling state whenever we jump and touch the ground again. The way this transition works is by having a trigger collider at the feet of the player, waiting for the on-trigger enter call whenever the collider enters the ground after jumping. Knowing that, we need two things: a trigger collider and a way to call the on-trigger enter method. Let's start with our trigger collider by going back into Unity. Selecting our player game object, create a new child game object and name it trigger checks, or any other name you'd like for colliders that will check for something. Inside of this trigger checks game object, create yet another child game object named ground check. Adding a collider in a different game object allows us to add a specific layer to it, which means we can control what a specific collider collides with. In the ground check game object, add a new component of type box collider. A sphere will likely be fine as well, but I'll go with a box. When that's done, make the collider a trigger by ticking the isTrigger checkbox. Right now though, its center and size aren't the most correct, so edit the center to be 0, 0.1, 0, and the size to be 0.25, 0.2, 0.25. It shall now be positioned around our feet and just slightly touching the ground. If your capsule collider height is still at 100%, make sure this collider is able to touch the ground by updating its center or Y size if necessary. When that's done, we'll add a layer to this collider game object, so add in a new layer named Ground Check. When you are done adding it, go to Edit, Project Settings, and Physics, and in the layers at the bottom, make sure you disable every collision for the ground check layer, besides collisions with the environment layer. This ensures that our trigger collider can only collide with the environment, meaning that other game objects, such as other players or enemies, won't call the onTriggerEnter method when being collided with. With our trigger collider added, we can now add the onTriggerEnter method. To do that, open up the iState script. In here, add in a new public void method named onTriggerEnter. Unity MonoBehavior onTriggerEnter method requires a collider parameter, so pass in collider as a method parameter. Make sure you import any necessary namespace. When that's done, open up the player movement state script and implement the onTriggerEnter method, making sure you add it to the iState method region and remove whatever code is inside. Make it a virtual method as well. With that done, open up the state machine script and create a new method to call the onTriggerEnter method by typing in public void onTriggerEnter collider. Make sure you import the necessary namespace. Inside, call in currentState.onTriggerEnter and pass in collider. Then open up the player script. In here, under the start method, call in the MonoBehavior onTriggerEnter method. I'll rename the parameter to collider instead. Inside, we can simply call in movementStateMachine.onTriggerEnter and pass in collider. All that's left now is to check if we collided with the ground and transition to the idling state if that's the case. To check for that collision, we can either use tags or layers. To be honest, I couldn't find which one is the best for these comparisons. So I'll go with layers by using a LayerMask to compare them, simply because layers seem to be the most related to collisions. Unfortunately, we can't or shouldn't really compare a LayerMask with a collider layer right away, and it's a bit bothersome to compare them when you don't understand how it works. But I'll try to explain it as best as I can. Before I explain it though, open up the player layer data script. This is where our ground layer reference is in, and we'll now add a new method that allows us to compare layers, or more specifically, check if a layer mask contains a certain layer. To do that, create a new method by typing in public bool contains layer and pass in LayerMask, and int layer. Inside, we simply return, between parentheses, 1 lesser than layer ampersand LayerMask, and outside of the parentheses, different than 0. Now, if you have never seen this before or never compared layers before, you are likely completely lost on the meaning of this return statement. To be honest, I was too and had no idea what this meant. To be able to fully understand it, let's go bit by bit. We have layer masks and we have layers. If you remember the layer inspector, you know that we can have up to 32 layers, some already used by Unity. This is basically a 32-bit bitmask. In human readable numbers, these layers will be represented from 0 to 31, which is what people often use in their code. However, let's take a look at our environment layer in computer numbers. Using the inspector 32-bit bitmask, it will be represented by a bitmask with a 1 at its 7th position. This is because our environment layer is the layer 6 in the inspector, and because layers in the inspector start from 0, the actual position is that number plus 1. Of course, our ground check layer will have a 1 in the 8th position instead and so on. So that's how our layers are represented in the 32-bit bitmask. A layer mask is also a 32-bit bitmask. If you remember from our inspector, a layer mask can be used to select multiple layers. So while it starts with zeros for the whole bitmask, the moment we select one or more layers in the inspector, the 32-bit bitmask will start turning zeros to ones in the respective layer position. For example, selecting the environment layer will have a 1 at the 7th position. Now, if our layer mask bitmask is looking the same as our layers bitmask with our environment layer selected, why can't we compare our layer with our layer mask? The reason why is that while layer masks are represented with computer numbers, layers are represented with human numbers, simply to make it easier for us to understand them. So, when we compare the environment layer with a layer mask, we are comparing a human number with a computer number, which won't work out very well. For raycast cases, because we are passing in the human number to the layer mask argument, that human number will be converted to a computer number represented by the layer number. For example, if we passed in 6, as that's our environment layer number, it will be transformed into binary and will be represented by a 32-bit bitmask with a 1 at its 2nd and 3rd positions. This is because 6 in binary is represented by 110. That 110 will then be transformed into a 32-bit bitmask as the raycast requires a layer mask. Of course, this will simply add the remaining bits or zeros to its left side. If we now compare it with the layer mask bitmask, we can see that they do not look the same at all, even though we've passed in the correct layer number. The fix to all of this is quite simple. We simply need to convert our human number to a computer number, which is what our weird formula does. Starting from the beginning, our 1 represents the first position of the bitmask. The lesser than sign is called bitwise shifting. Simply put, we tell our bitmask to shift an amount of times to the left. So our 1 that was in our first position will now shift itself layer amounts to the left. If our layer is the environment layer, then it will shift itself 6 times to the left, which means it will now be in the 7th position. With this, our human number is now a computer number, and represents the same bitmask that our layer mask represents. This means that comparing them will give us the desired result. However, remember that a layer mask can contain multiple layers. If we were to also add in the ground check layer, it will now have a 1 in the 7th and 8th position, which will now be different than our environment layer bitmask. That's where the ampersand layer mask comes in play. The ampersand sign is a bitwise operator and represents the AND operator. This operator will compare all bits in both of our bitmasks and return 0 when one of the same position bits is 0, or 1 when both bits are 1. Simply put, it keeps the common ones between both bitmasks. If the returned bitmask has any 1 in it, then it means that if we convert this Bitmask computer number into a human number, it will return a value over 0. For example, in this case it will be 64 as it's a 1 in the 7th position. This means that our layer mask contains a passed-in layer. If the final bitmask were to return a bitmask with only zeros, then it would mean that the layer wasn't part of the layer mask. That's what our different than 0 is for. Again, if the final human number is 0, then it means the layer mask didn't contain the passed-in layer, as there was no 1 in the same bit in both bitmasks. If the final human number is different than 0, then it means the layer mask contains the passed-in layer, as there was a 1 in the same bit in both bitmasks. I'll leave a few links in the description if you want to dive deeper into it, but it should be enough for you to understand our use case. With that in mind, we'll also create another method to check if it's a ground layer. So type in public bool is ground layer and pass in int layer as a parameter. Inside, return contains layer and pass in ground layer and layer. That's all we need here, so now open up the player movement state script. In our onTriggerEnter method, we'll check if the object we have collided with is part of the environment by typing in if statemachine.player.layerData.isGroundLayer and pass in collider.GameObject.layer. Inside of this if statement, call in a new method named onContactWithGround and pass in collider as an argument. Return right after to make sure nothing else gets called. I'll make the method protected virtual and add it to the reusable methods region. We'll override this method wherever we need something to happen when we enter in contact with the ground, which we don't need in our movement state. We can use this method to transition to the idling state in our jumping state, but because I know we'll need to transition more times to the idling state, or more specifically to the light landing state whenever we add it, we'll actually add it to the player Airborne state script, so open it up. In here, create a new region named Reusable Methods. Inside, override the onContactWithGround method. Then transition to the idling state by typing in statemachine.changeState and pass in statemachine.idlingState. Feel free to remove the base method call as well. This should be enough to test our current jump. So save it all up and go back to Unity. If we enter play mode, our jump should now work and its force should depend on the current player state. We also cannot move mid-air. However, we still need to finish up a few features from the jumping state. Automatic rotation, force modifier when on a slope, fixing the floaty jump feeling, and keep sprinting after jumping. We'll start with the automatic rotation, so go back to the player jumping state script. We need to automatically rotate our player if we have entered the jumping state with a movement input key pressed. Not only that, but currently we are always jumping to the player facing direction. This is not what should happen when we press a movement key, and should instead jump towards our movement input direction if that's the case. We'll start by creating a variable to know if we should rotate, so above type in private bool should keep rotating. Then in the enter method set the should keep rotating to be equal to statemachine.reusabledata.movementInput different than vector2.0. This makes it so we keep rotating if we have input. With that, we can now override the physicsUpdate method and inside type in if should keep rotating. If that's the case, we can call in rotate towards target rotation. We are adding it inside of the if statement, as we'll have another if statement in this method later on. We shall now make it so that the player jumps towards the movement input direction instead of the player forward direction if we enter the jumping state with a movement key pressed. To do that, go to the jump method. The way we'll do this is by updating our player forward variable value to be the movement input direction instead when we have a movement key pressed. We can use the showKeepRotating variable to know if our movement input key was pressed, as that's the condition we gave it in our enter method. So after our player forward variable, type in if should keep rotating. If that's the case, we'll update our player forward to be the movement input direction. However, we actually want the direction to be relative to the camera, as the movement input will be in world space. We can do this by getting the direction of our target rotation, which was updated when we moved before jumping. We also have already created a method before that guesses a direction given a rotation. So simply type in player forward equals to get target rotation direction and pass in statemachine.reusabledata.currentTargetRotation.y. This is a method that transforms a quaternion with a certain angle into a vector direction. Remember that even if we come here from a stopping state, we enter them with an updated target rotation already, so we don't need to update it here. Our player forward variable name no longer makes much sense, so we'll select it and rename it by pressing F2 or right-clicking on it and choosing rename, and set its name to jump direction. Of course, like we've seen before, both dashing and jumping have a different reach time, so we need to set that up. To set it up, open up the player jump data script. In here, create a new property by typing in field, serialize field, public, player rotation data, rotation data. I'll give it a private set. When that's done, save it up and go back to Unity. In the second inspector tab, set the jump data Y rotation value to be 0.02 seconds. Then go back to the player jumping state script and create a new variable above by typing in private player jump data. Then in the constructor, set it to be jump data equals to airborne data.jump data. In our enter method, we can now type in statemachine.reusabledata.rotation equals to jump data.rotation data. We should also not forget to reset this rotation data when exiting, so override the exit method and call in setBaseRotationData. If we save it all and head over to Unity, entering play mode should now have our jump working fine. That's great, but we shall now make sure we have a lower jump force when on slopes to make sure we don't get into the slopes when jumping, which will make the player look like he's sliding. This mostly happens on steeper slopes. To do that, head back to the player jumping state script. We'll do this by casting a ray in our jump method to know if we are on a slope and then update the forces if that's the case. To do that, before resetting the velocity, type in vector3 capsule collider center in world space equals to statemachine.player.collider.utility.capsulecolliderdata.collider.bounce.center. Then create the ray by typing in ray downwards ray from capsule center equals to new ray and pass in capsule collider center in world space and vector3.on for the direction. We can now cast our ray by typing in if physics.raycast and pass in downwards ray from capsule center and out raycast it it. We need the distance of our ray now, so open up the player jump data script. In here, type in field serialize field range from 0f to 5f, public float, jump to ground ray distance, with a private set. I'll default it to 2f. When that's done, go back to the player jumping state script. Pass into the raycast jump data .jump to ground ray distance. For our layer mask, we'll pass in state machine .player .layer data .ground layer. Then pass in query trigger interaction .ignore to ignore trigger colliders. If we hit something with this ray, we then need to know if we are on a slope. We'll of course be using the vector3.angle method again. To do that, type in float ground angle equals to vector3.angle and pass in it.normal and minus downwards ray from capsule center .direction. We now need a way to check for the angles and set the force accordingly, which we'll be doing by using animation curves. However, we'll need to create an animation curve for both going up and down slopes. This is because that's how it works in Genshin. When going up, we update the horizontal forces to make sure we don't slide in the slope. When going down, we don't really need that as there is no ramp in front of us, but it seems that they update the vertical force to be a bit lower. To know whether we are going up or down, we simply need to check the player vertical velocity. Going up means it's positive, while going down means it's negative. We'll create two methods for that, so open up the player movement state script. In the reusable methods region, head over to the isMoving method. Then create a new method by typing in protected bool isMovingUp and pass in float minimum velocity defaulted to 0.1f as a parameter. Inside, we can simply return getPlayerVerticalVelocity .y greater than minimum velocity. That's all we need, so now duplicate this method and rename it to isMovingDown instead. Then we'll swap the greater than with lesser than and add a minus sign before the minimum velocity. This makes it so that we can pass in a positive velocity as an argument, while the method takes care of it being checked as negative, which is what should happen. When that's done, go back to the player jumping state script. In the raycast if statement, now check if isMovingUp and also if isMovingDown. We can now start creating and setting the animation curves for each situation. To do that, open up the player jump data script. In here, create a new field serialize field public animation curve jump force modifier on slope upwards and give it a private set. You can give it any other name if you find something better. Then duplicate the property and swap upwards with downwards. When you are done, save everything and head back to Unity. In here, open up the second Inspector tab. In the Jump Data area, start by opening up the Upwards Force animation curve. Select the first curve preset. Then right-click on the last key, press Edit key and set its time to be 90. We'll have two different ranges. From 20 to 35, the force modifier will be 0.75, or 75% of the original jump force. From 35.1 to 75, the force modifier will be 0.5, or 50% of the original jump force. This is because the steeper the slope, the easier it is to look like we are sliding. So we need to make sure we have a lower horizontal force. Knowing that, add in 3 keys. $20 with a value of 0.75, 35.1 with a value of 0.5, and 75.1 with a value of 1. Of course, we don't want this to look like an actual curve, so select all keys and set both tensions to constant for all keys. If all has been done correctly, 20 to 35 should be at 0.75, 35.1 to 75 should be 0.5, and the rest should be 1. With that done, close the current animation curve and open up the downwards animation curve. Choose the first curve preset and change the last key time to be 90. We'll only have one range here. From 20 to 70, the force modifier will be 0.85 or 85% of the original jump force. Make sure the 70 key is actually 70.1 and set to 1, for the reason as all the other animation curves. Set both keys' tensions to be constant. We should be left with one single area from 30 to 70 set to 0.85, and the rest set to 1. That's all we need for our animation curves, so feel free to close it and head back to the player jumping state script. In our isMovingUp if statement, we'll need to apply the forces only on the horizontal axis. To do that, start by typing in float force modifier equals to jump data dot jump force modifier on slope upwards dot evaluate and pass in ground angle. Then apply the modifier by typing in jumpForce.x multiplied with force modifier and jumpForce.z multiplied with force modifier. That's all we need when moving up, so in our isMovingDown if statement we'll need to apply the forces only for the vertical axis. To do that, copy the first two lines of the isMovingUp if statement and paste them in the isMovingDown if statement. Then swap upwards with downwards and x with y. This should be all that's necessary to correctly jump on a slope, so save it all and go back to Unity. Entering play mode, we shall now be able to jump correctly in both of our ramps. We should also be jumping differently when going up or down the ramps. Do note that animations also play a part on how good this looks, so you might need to update the values once you add animations into the system. If it isn't working in your own game objects, make sure that ramp angles are within the ranges we have added, as if they aren't, they will jump normally. I think you could ramp up the 20 to 30 if you'd like, but I made it 20 so that we could test it out in our current ramp, as 20 shouldn't be steep enough to need a jump force modifier. With that done, you might have also noticed that our jump looks kinda floaty. If we take a look at Genshin, if we jump, we see that it gets to the top quite fast, not really having much of a floating feeling. And yes, I'm still talking about the jump. The reason why the jump feels floaty is because it's taking its time to get to the top, and then gravity also takes its time to create a strong enough negative velocity. The way we'll make it less floaty is by adding a small negative force while the player is going up. This makes it so that we get to the top faster, which makes it look less floaty. You could also add a small negative force when going down, which will make the player fall faster, but I'll just add one when going up. To do this, go back to the player jumping state script. In here, in our physics update method, type in if isMovingUp. If that's the case, we need to add a force to our player vertical axis. We'll do that using the acceleration force mode, as we want to slowly decelerate our player over time. Of course, we currently only have an horizontal deceleration method, so we'll need to create one for a vertical deceleration. To do that, open up the player movement state script. In the reusable methods region, go to our decelerate horizontally method and duplicate it. Then rename it to decelerate vertically. Inside, swap the getPlayer horizontal velocity with getPlayer vertical velocity instead, and rename the variable to player vertical velocity. If you want this decelerate to always go down, then make sure you swap the minus sign to be on the force instead, as otherwise a negative velocity will become positive, which means it will make the player go up. Because I named it decelerate, this is what I'll have it do. This of course means that if our player was going down, decelerating it vertically will make it fall slower and slower over time. With that done, go back to the player jumping state script, and inside of the if statement, call in decelerate vertically. Of course, we need a value for the deceleration force, so open up the player jump data script. In here, type in field, serialize field range from 0f to 10f, public float deceleration force, and give it a private set. I'll default it to 1.5f. Back into the player jumping state script, in the enter method, set the state machine.reusable data.movement deceleration force to be equal to jump data.deceleration force. And that's all we need to make it less floaty, so save it all up and go into Unity. If we enter play mode, we shall now be getting to the top a bit faster. If you wanted the player to get there faster, you will simply make the force stronger. Although if you make it too strong, it will reduce the jump height. We are almost done with our jumping state, but there is one more situation to solve. If we take a look at Genshin, if we jump when we were sprinting, we will keep sprinting after landing. However, this only happens if we have held the sprint key long enough. If we didn't, then we'll go back to the running or walking state depending on the walk toggle value. We also do not keep sprinting with other states like gliding or hard landing or rolling. Of course, we still don't have this in our system, but we'll make it so that it only works for the jumping state. We'll be doing this by creating a reusable data property that defines whether we should keep sprinting or not. Then in our onMove method, if this property is true, we'll simply transition to the sprinting state. The property will only become true when we are sprinting and decide to jump. So, to do that, start by opening up the player state reusable data script. In here, duplicate the shouldWalk property and name it shouldSprint. When that's done, open up the player grounded state script. In the reusable methods region, go to the onMove method. In here, above everything else, type in if statemachine.reusabledata.shouldSprint. If that's the case, then we can transition to the sprinting state by typing in statemachine.changeState and pass in statemachine.sprintingstate. At the end, we return as to not call the remaining statements. When you are done doing that, open up the player sprinting state script. In the input methods region, in our onSprintStarted method, type in statemachine.reusabledata.shouldSprint equals to true. The reason why we are adding this here instead of in the onJumpStarted method is because we only want to keep sprinting if the sprint key was held enough time, which we won't know if that's the case in the onJumpStarted method. You could do it in the onJumpStarted method by checking the keep sprinting variable value if you prefer it to be that way. Above, in our variables, we'll create a new variable by typing in private bool should reset sprint state. Then, when we enter the sprinting state, we'll set the should reset sprint state variable to true. When we exit the sprinting state, we'll check if should reset sprint state. If we should reset it, then we set our keep sprinting to false and our statemachine.reusabledata.shouldSprint to false as well. In case we shouldn't reset it, we want to keep these variables as they were, which makes it so we start sprinting once we land. Of course, we need to set this variable to false somewhere, and we'll be doing that when we jump. So in our input methods region, override the onJumpStarted method. Then, before our base method call, we type in should reset sprint state equals false. The reason why we are doing this before our base method call is because on the base onJumpStarted method we are transitioning to the jumping state. This means that our sprinting state exit method will be called before we set the should reset sprint state variable value to what we want. Now, while everything seems okay so far, let's say we enter the jumping state with the should sprint property set to true. Whenever we come back to a grounded state, we'll enter the sprinting state due to the onMove method. However, let's say that while in the jumping state, we were to start gliding whenever we add gliding to our system. In Genshin, this makes it so that we no longer go to the sprinting state whenever we land. But because we are not resetting it anywhere in our jumping or airborne states, right now we'll always come back to sprinting. To fix this, open up the player airborne state script. In the reusable methods region, create a new method by typing in protected virtual void reset sprint state. Inside, we'll call in statemachine.reusabledata.shouldSprint equals to false. Then call this method in the enter method, which we need to override. I'll also add the enter method to a new region named iStateMethods. This makes it so that every time we enter an airborne state, the shouldSprint property gets reset to false. Of course, we don't want that to be the case on the jumping state, so open up the player jumping state script and create a new region named Reusable Methods. In here, override the reset sprint state method and leave it empty. Now every airborne state besides the jumping state will reset the shouldSprint property. However, we still have another problem. While we'll indeed keep sprinting after jumping and landing, this currently stays true even if we stop pressing the movement keys. In Genshin, we'll only keep sprinting if we never let go of the movement keys, or more specifically, if a movement key was pressed when we landed. If we do land with no movement key pressed, then when we move again, we'll go back to the normal running or walking states. To fix this, open up the player grounded state script. In here, override the enter method. Inside, we'll call in a new method named update should sprint state. Inside of this method, we'll check if not statemachine.reusabledata.shouldSprint and return if that's the case. We'll also check if statemachine.reusabledata.movementInput is different than vector2.0 and return if that's the case as well. If none of these are true, then we'll reset the shouldSprint property by typing in statemachine.reusabledata.shouldSprint equals false. This makes it so that every time we enter a grounded state, if our shouldSprint property is set to true and there is no movement key pressed, we set the shouldSprint property to false. which means we won't transition to the sprinting state. I'll also add this method to the main method's region. That's all we need to do for our jump. Of course, we can't really test this out until we add animations, but it should be working fine.